I'm Bergen from Los Alamos National Laboratory, and Tim told me I needed to try and be fun, so we'll see how it goes. My talk is called Lies and Deception. I really like OpenCL, and I have for a long time because I did a lot of work on Roadrunner, and when OpenCL came along, it kind of addressed a lot of the issues that we had to deal with that architecture, so it just made sense. So whatever thing comes out of this, OpenCL looks a lot like what I think we need. So I think there was a lot of FUD about OpenCL in the beginning, kind of manufactured concerns about it that are maybe not real. So to address this, and I hope this works with my speaker, because I have sound effects. We have Wheel of Fortune. So I'll be your host. I hope you know Wheel of Fortune. We're going to play like the lightning round where I fill in letters. You guys have to guess it. If you get the right answer, then you'll probably get a prize. T-shirts. So we've got FUD 1. Okay, you ready? Just call out the answer.
OpenCL is slow.
Hard. Who said hard? OpenCL is hard. This is not exactly true, though. So I like this quote from Einstein where he said everything should be made as simple as possible, but not simpler. So he was a smart guy, and I think that I read an analogy in HPC Wire sometime last year where a guy compared scientific computing to our history in aviation. So we've got Orville Wright back there with his broomstick to steer the airplane, and that was sufficient for that model. The analogous thing in supercomputing today would be something like the space shuttle, and you wouldn't expect for one guy who flies a Cessna to be able to operate the space shuttle. It takes a team of people to deal with all of the aspects of that. So I think that there's an analogy in supercomputing that we're trying to solve some of the hardest problems that there are, and we need tools that, for the right people, expose kind of the details of the architecture so that we can do them. So I don't think it's reasonable to expect for a domain scientist to really be able to get, the full impact out of these systems that we're building. And so with that said, I think OpenCL gives us some tools that we need. So these are some of the things that we kind of identified when we were doing Roadrunner development that are important for being able to develop portable codes, at least. So short and wide vector. With the mic architecture coming out, we have these 512-bit wide execution pipelines, and we're likely to see a lot of these wide vector things. So in order to get performance, we're going to have some kind of intrinsics. If we've done that, we can at least get some use out of the types and intrinsics that are defined in OpenCL and get some portability. For memory model and data movement, we have explicit control in OpenCL, so we can do read and write kinds of functions. We did some experiments on the fusion parts to look at what happens with the zero copy memory and using map and unmap. We also looked at CUDA. That actually does quite well in some cases. So it's a lower cost or kind of lower investment to be able to do that without doing the explicit copying. And then for fusion parts like fusion and maybe the Ivy bridge, where we have really a single address space, I think OpenCL will add support for some shared virtual memory stuff so that it'll make it easier for that. So, I mean, the point of that, I guess, is that you have different levels that fit whatever it is. If you really have a discrete address space, OpenCL gives you a tool and a way to control that data motion. And if you don't need to do that on your architecture, you don't necessarily have to dive down that far. The execution model gives us a nice data and task parallel programming model. We can do fairly rich things with the task concurrency models. I have a couple of slides about programming ideas for how we would use that. That should, you know, I don't know, it'll allow us to do more things. And one way to find concurrency is to do operations that were serialization points before in a code. If we now have tools like being able to split up a processor into logical devices, we can task those separate parts of the device to do things concurrently, like checkpointing or diagnostics. I think the one thing that's lost on people is that a lot of people seem to think that OpenCL is just a way to program accelerators, and I actually see a lot of its value as being kind of the event and scheduling layer of the runtime, because that's something that you have across all these different architectures. So instead of using, you know, pthreads in one place and maybe TBB in another place, you have all of these different things for different architectures. With OpenCL, that kind of higher level scheduling is consistent, and so you have, you know, you can have a foundation on that, and then if you need to, then you can go down and implement something specific for an architecture. Okay, so we've got the next question. I didn't give, who said hard? T-shirt.
Oh, not those.
No? These?
Those are the fat boy shirts.
Oh, okay.
We have fewer of those.
All right, so here comes the next one. You ready? This one's hard.
What's the question?
It's a FUD, a thing that people say.
OpenCL is not for the
Portable permanent.
Who said that? Ah, okay, you get it. OpenCL is not portably performant. That's what people say. I don't really agree with it. I think this is my analogy. The thing that can't fly is telling the thing that can fly, you know, it's criticizing it for not being able to fly to the moon. So, is this the real intent of this complaint? I think it's more maybe to say that OpenCL is not performant. And I personally, at least, have not seen that. We get good performance per architecture, and it misses the point that the power of OpenCL is that if you need to do a special implementation for some architecture, you can really go down as far as you need to get performance. I mean, you could be calling assembly instructions, or with this custom device support, you could be calling something on FPGA, and again, you have kind of this event structure and calling structure of the runtime that is portable across different platforms, with interrogation of the runtime system to decide what kernel you want to run on it. Question?
So I've been doing OpenCL development for the last 2 years, and I've been doing it on Intel and Apple and AMD and NVIDIA, on Linux and Windows and Mac OS, and I've been testing a bunch of different kernels on all of these and trying to get performance and portability. And what I'm finding is that it's not shocking that unless you know specific things about each individual architecture and each specific implementation, you're not going to get optimal performance on any one of them. But you certainly can get reasonable performance in a short amount of time, the same way you can with CUDA, the same way you can with directives, and the same way you can.
Could you get optimal performance if you really made, you know, a tuned kernel for that architecture?
Sure, you can say inline PTX assembly in NVIDIA, for example, and you can.
Right.
And
I mean, in my job, you know, for general stuff, it may not make sense to do that. But if we get a big machine that has a particular type of processor, then we can invest 3 or 6 months in tuning it. But I guess what I would say in support of OpenCL is that that higher level infrastructure doesn't have to get changed every time. And that's what we've had to deal with in the past.
That's fair.
That's my guess. Okay, question?
To extrapolate on that, I would say that you're describing not portability though, that the idea of portably performant must include performance in my portability. If I can write an average program that runs everywhere, that's useful, but it's not a performant program that runs everywhere. And I reviewed a couple of papers this year, all of which pointed at the idea that you run everywhere works, but you're looking at a factor of 2x on the table if you don't retune it. And I guess maybe it's semantics of performance, but it's portable but not performance. It's not quite the same thing.
Well, I'm not claiming that OpenCL is portably performant. I think that it's FUD because it's the wrong question to ask, and it's not. I mean, if I could just get something where that allows me to detect what platform I am on and optimize for that platform without changing, higher level things about the code, that's worth something.
I gotta jump in here.
Okay.
I get so sick of the portable performance issue because let me tell you something. Do you have portable performance anywhere?
No,
you do
right.
if you call
Yeah.
applause.
There is no such
I hear
thing.
people say, well, on my CPU, I can run from an AMD CPU to an Intel CPU. It's like, yeah, you're getting 1% at peak, maybe 3% at peak. But if you're talking about getting high fractions of peak performance on any platform, I'm sorry, you're going to do tuning. There is no portable performance, period. Don't blame OpenCL, blame all of us. Just the computing world does not give you portable performance. To expect OpenCL to do better than the world with C or C++, the general world of CPUs, just doesn't make sense. It's FUD designed by people who are trying to block OpenCL for evil, dark, nasty reasons.
I agree. That's why I picked it up.
Well, I think if it was made portably performant, we would run out of jobs. So,
That's true.
Good
Yeah.
Exactly.
To help the portability of performance, could we have some standard way of when our OpenCL kernel is being compiled, have some pound-defined directives to say which kind of architecture is being compiled for? Not all of the vendors expose that. Because AMD one, you can get which device you're being, pound defined about what device you're being compiled for.
So you have a preprocessor
Yeah,
thing that you can
preprocessor.
switch
So I
off.
can just turn off, put an if-def around a critical piece of code, so I can not have to write a whole other kernel. I can just know that it's compiled.
Well, I mean, that's a compile time consideration. Well, no, I guess it's a runtime consideration though in OpenCL for compiling that dynamically.
So you're saying you want a pound-defined preprocessor in the kernel programming language so you can build optimizations in. Okay?
Okay.
But you don't need that. 'Cause you can already do that by taking, in your host, you can say, oh, if I'm this, I compile that with, and you pass the string, -d, whatever you want, and then you can do it yourself.
Yeah, I parameterize my
but that's not-
compiles.
It's still awkward to do.
It's
because
awkward,
It'd be nice if it was part of the language.
It would be nice if
Because
You would like
Carl's
some
did.
you would like a standard in the actual OpenCL
Right.
the OpenCL C compiler language that specified these preprocessor
Things like
defines.
CUDA that gives you that compute capability 1.0, 1.2, they've got pound defines for that. And AMD has which specific, if you're on a Cayman or a Turks or whatever, it's not standardized, and so I have to either do some of it at the host, which again, it's just sort of random strings as far as what I see, as far as what version I get. There's nothing clean I can put in my code that will work portably right now. You can do some of it at the host, and you can do some of it inside your CL kernels. I just would like to have something that's more standardized.
Okay, thank you.
We heard you.
While we're on wish lists, debugging is a big problem. We've got to deal with it. I don't mind debugging on x86, but right now, even with the AMD x86, I can't even see local variables. They still do optimization when they compile the kernel.
Right.
Someone's
Okay.
got to fix it. The Intel one also doesn't allow you to jump in.
Well, that's easy. Just stop writing bugs.
I promise you, next year I'll stop writing bugs.
Okay.
So I got lost on my slide here. I have kind of a programming model thing that I've shown before that'll talk about how I envision using some of the task concurrency in OpenCL. I think I said something about the memory model being somewhat flexible. We have this abstract memory model. It should be able to be extended for new kinds of architecture. So now we have the last round.
OpenCL is the future.
Yes. That was fast. Okay. So I agree with this one. Or at least I think the future looks like OpenCL somehow. So the last thing that I have is just a few slides about kind of the difficulties that we face in programming for all these architectures. I just actually found out something that really irritates me. Apparently the mic device runs an operating system.
Don't look at me. I'm in the lab. I have nothing to do with Mike.
I think that's really unfortunate. I was hoping, I mean, I worked at Los Alamos, I was hoping that we would never see another machine that looked like Roadrunner. And I have to actually, I have to do a cosmology code on this Stampede machine, probably. And it looks like I'm going to have a host processor and then another thing running a Linux operating system, so I have to whip out some kind of relay between those. It's a layer in the that I don't want, that's not included in my picture, but this is supposed to represent kind of a standard cluster that then may have different architectures in it, so it could be a hybrid node that mixes at least different OpenCL platforms, so it used the ICD to handle that. And you know, here are some of the kinds of parallelism that we have to deal with. We have distributed memory parallelism between nodes in the cluster. I would inject some kind of task parallelism in that, so if I do have these two different architectures, I may use them in different ways. If I dive down lower, I have superscalar, I have instruction level parallelism, and a lot of these I have some kind of SIMD or wide vector thing that I have to deal with. So how do I do that?
You have a question?
I'm sorry, yes, what's your question?
So why is having the operating system on mic a problem? Can we see that
Because I can't, so if I have a cluster of things that have CPUs or have a GPU of some kind and I use OpenCL, then there's an ABI and I can just use OpenCL to launch and control processes that execute on that device. If I have a host process and then something that's running an operating system, now I have to do something like message passing to
No,
get...
you don't. OpenCL will run on mic.
Will it run on mic from the host processor?
Yeah.
Okay, sorry.
Absolutely.
This is my ignorance then.
Absolutely.
I just found out about this. Okay,
Yeah.
so I can bypass that.
Yeah,
I don't have to talk to that
I thought you
thing's-
were worried about the overhead of running the OS on there, and I'm like,
No.
yeah, probably, but yeah,
No,
no.
not so much.
Also, Hebrew University has a package that lets you run OpenCL across multiple nodes as if you're running it on a single node.
Right, they won an award from us last year.
Right.
Okay.
Great package.
That's just my...
Okay.
Okay.
Yeah,
Sorry.
Mike is wonderful.
I
You're
didn't
supposed to
mean
just say it's
confuse
great.
that. Mike is great.
Yeah. It's off. Yeah.
No, I have one of those. I mean like an Intel shirt.
I don't
No, I'm
have.
with Mike.
I'm in the labs. We don't do
Go
that
with the
stuff.
mic.
Okay, so if in this thing, then here I can, my idea is that, you know, I would use OpenMPI somehow to do this distributed memory stuff, and then within a node, OpenCL gives me kind of all of the control that I want to handle different heterogeneous looking nodes and devices that might be there. So I can handle, you know, with the enqueuing ND range or enqueuing a task, I can deal with data and task parallel stuff. I have generic types and intrinsics for doing the SIMD, and so I can really kind of program within a node while doing that. And then a lot of our codes use OpenMPI, so I have a way to do that too.
Awesome.
I have a little idea here going back to this being able to split, having a logical device off of an actual hardware device. I like the idea of being able to split things up into logical queues where I may have kind of a performance queue that's doing the simulation, and then I have auxiliary queues where I may use cores or a separate GPU to do rendering diagnostics or something, and that can happen concurrently on the node. So, question?
Yeah, I had a question from the previous slide. How portable is the SIMD support? You mentioned intrinsics. Do I use like the Intel intrinsics, or is it?
So OpenCL
So
has
OpenCL
types and
intrinsics.
intrinsics that are I guess a subset of
Yes,
the
full kind
of the different intrinsics in SSE
We have vector. There's a vector type and vector operations defined in the OpenCL kernel programming language.
And they're portable. I can run on.
Portable.
Yeah.
Okay.
That's right.
Yeah. You could still, I think you could still call, if you knew you were on one and you needed an intrinsic to get performance from SSE or AltaVec or whatever, I think you could still directly call that, couldn't you, from within the OpenCL kernel?
I've never tried it. I don't know.
Okay.
I don't know.
There's no OpenMP in that picture. You think that you can?
I don't really like pragmas. So maybe Benedict should be down here. But
Pragmas are wonderful.
I mean, you could substitute OpenMP maybe for that model, but you wouldn't have the same kind of control.
I guess I'm wondering, are people going to need 3 levels to parallelize across the cluster on the across the SMP nodes across the accelerator? Or do we think that OpenCL is going to be able to control all of that?
I think OpenCL would be able to control that.
So let me ask a broader version of a broader version for that. If I have a homogeneous platform today, I do have a solution called OpenMP. What do I give up and what do I gain by going from OpenMP to OpenCL?
So if you have a homogeneous cluster, you may not care as much about something that has discrete memory on it. And so with OpenMP, I think you're relying on the compiler, or you use your pragmas and you identify something that could run on this device. But now, I don't think in OpenMP that you have as much control over data motion.
So OpenMP is a restricted class of platforms, cache coherent, shared memory, and if that's all you're planning to target, then you probably should not change from OpenMP. OpenCL will run on a shared memory, shared address space system, but it'll also run on these devices with that are more GPU-like or more many-core-like with more complex memory hierarchies. So it's a broader range of systems.
Right, but so I start, and then I think you answered the question. You said if my platform is homogeneous shared memory, even you wouldn't move.
Even I wouldn't move.
Okay.
But I'm part of the OpenMP group. I'm part of the OpenCL group. I love OpenMP. It's great. All I ever do in my life is just change the last 2 letters from MP to CL.
Are they adding any support to OpenMP for?
Yes, in OpenMP we are, OpenMP for the last 3 years has been working on a pragmas that will launch work on an accelerator, on an attached accelerator. It would be, the goal is to have that in the core OpenMP specification by the 4.0 time frame, which will be in about a year. There's a group called the Open Accelerator Group, which has released that specification. It's PGI, Cray, and a few others, to try and get people out there and using it now. But I should not be talking about that now, because this is the OpenCL BOF. And gosh, don't use OpenMP, only use OpenCL.
Okay.
I gotta remember where I am.
Someone has one more question, because I'm going over time here.
You are.
Yes, I have also a question concerning SIMD. I mean, different architectures have different SIMD widths, so I don't really want to write float 4 code, because I know, like, the future AVX, for example, will execute 8 of them at the same time. So why not write just scalar code, and if it's independent, the compiler can put this together and kind of issue the correct intrinsics from it?
Do you believe that'll work?
So Intel right now does that. We call it implicit vectorization, and it works well-ish and getting better. There are cases where I show that we get 65% of hand-toned SSE intrinsics from the implicit vectorization. So it works, and it's only going to get better. So it is my long-term hope that I'll be able to tell people, do not use the vector intrinsics in OpenCL. Only write your code with scalar as if you were writing it for a GPU, and yes, indeed, our compilers will take care and use the vector units. In fact, I think in the long run, OpenCL for the CPU world may be more important for vectorization than anything else. So, and I really believe that that could, in the long run, be the most important use of OpenCL for us.
I've had trouble with auto vectorization of things that aren't like single-strided before, so I don't know. I mean, I guess I would say that OpenCL allows you to then choose if you detect that you're on that architecture. Maybe you can go without doing the vectorization. You find something where you're not getting the performance because of that, you could implement that kernel then. Okay.
It would help a lot if we got feedback on how well the vectorization went.
Well, Intel's compilers actually do a pretty good job.
I don't get any feedback from it. How do you get feedback from it?
So on the
end,
well, I'll tell you, you're either going to hate this or love it. We have in our OpenCL SDK an offline compiler tool where you can basically highlight the text of a kernel, drop it into a box, and it'll show you the associated assembly code.
Wow, I didn't know that. I've been using it for a while. Okay, I'll try it.
Yeah. But the reason I said you'll either love it or hate it is if you like reading assembly code, you're like, man, that's exactly what I want. If you don't like reading assembly code, you'll go, a lot of good that just did me. Yeah, okay. So tools are where you'll see a lot of evolution.
Like your regular compiler gives nice feedback about vectorization.
It does.
The AMD SDK also has the identical thing, which does their GPUs for a whole variety of GPUs, the low-level instruction IL, as well as for CPUs, the x86. So you can see the exact same thing. It's called the Stream Kernel Analyzer, I believe.
Okay, thank you. I'm glad you mentioned that. So,
got one back there?
Yeah.
Hi, I have a question. How do you compare in terms of portability and programmability of OpenCL and CAPS-based HMPP?
Are you asking me? Charles Fairmont is a scientist in XCP division. He's tried CAPS, and he kind of came from
the OpenMP and Pragma-based stuff, and he liked CAPS, so he thought it was cool. But as far as I know, there hasn't been any kind of rigorous analysis done in comparing performance. So I can't answer that.